Pulleys are another example of our connected masses, and you often have a really good sense of how these work without thinking about the physics. So here's an example. This is sometimes also called an Atwood machine. So just be aware of that if you see it. Okay, so in this example, we've got a 12 kilogram mass and a 4 kilogram mass. You can probably imagine that if we were to set this up, and we're assuming that our pulley is frictionless and that our strings have no mass. We've sort of been assuming that the strings have no mass this whole way. You know, if you set this up, it's going to start doing this. The 12 kilogram mass is going to pull the 4 kilogram one to the ground. This is a lot like our previous car examples, car and towing, except now we've got two driving forces acting here. The first driving force, let's call this one mass 1, and we'll call this one mass 2. The first driving force is going to be m2 times g, the force due to gravity acting on this block here. And the other driving force we're going to have acting is this one, m1g, the force due to gravity acting on this block here. There are also two tension forces that are acting, and the tension forces are got to be equal. If they were different, the rope would break or the two masses would weirdly get closer to one another. So, it's like we've got a car example, but we've got two driving forces here, m2g and m1g. Now, they're going to counteract each other, so that it's going to slow each other down. And we've got these two tension forces acting in the end, Ft, Ft. For this question here, you might see that the first block is going to accelerate in this direction, and the second block is going to accelerate in this direction. So our sign convention is going to look a little bit weird, but it's going to be positive like this. On this side, it'll be positive in this direction, and on this side, it will be positive in this direction. Because remember, we've got to make it in the direction we're accelerating. I like to just draw something like this, an arrow going like this, but if that upsets you, you can draw two separate ones, one acting on this side and one acting on this side. I don't mind which you prefer. I'm lazy, so I'm going to do this. So, like I said, we could sort of undo this pulley and we could draw it as a situation like this. And with that one, the acceleration would be in this direction. Some people really like thinking about it like that. I had a student suggest that one year and I thought it was really neat, so I just wanted to mention that. I probably won't be drawing that again, but I really encourage you to if you find it useful. So with this question here, I haven't actually written what I want you to find, but I want to figure out the acceleration and I want to figure out that tension force. So I want to know what is A and what is this tension force. Now, there's three possibilities, I should say. We could do sum of the forces equals ma on this object here. The problem is two unknowns. Don't know the acceleration, don't know that tension. We could think, okay, let's have a look at this object here. We've got the tension that we don't know and the acceleration again. So what we're going to do is we're going to look at the system. And when we look at the system, we can ignore those internal forces. So sum of the forces equals ma. We've got to be accelerating here. And that's going to be on the system. Cool. So, which directions, which forces do we have? So ignoring these tension forces, they're parts of the system acting upon one another. So the only forces we've got is this mg and this mg for these two different masses. So, which one's acting in a positive direction? The m2g is, because we said this direction was positive. And we've got to do minus m1g because it's acting this way, and for this side, this direction was positive. Very good. And that's got to equal, now this one we've got to be careful, the mass is m1 plus m2 times this acceleration. I wish I'd written this first off to write this for the acceleration. So I wish I'd done A with sum of the forces on m, but oh, that's okay. We're going to do this in the next step here. So A is going to be m2g minus m1g on m1 plus m2. Now, you don't have to do this, but you could write that as m2 minus m1g on m1 plus m2. You might find it useful for a question like this to actually put this diagram clearly labeling which one is mass 1 and which one is mass 2, and the shortcut for finding this acceleration here. Really important you don't mess up which one is mass 1 and which one is mass 2. Mass 2 is the one that is the heavier mass here. So here, M2 is greater than M1. You might like to put that on your note sheet as a nice little shortcut for yourself. Am I going to run out of room? Oh no, I've given myself a bit of room. Okay, so let's actually calculate what this is. So we're replacing everything here. M2 was 12, minus M1 was 4, oh, I'm so sorry for one sig fig, everyone, times G, which was 9.8. I've just taken out G as a common factor from here to here. I might have glossed over that. And then M1 plus M2, we're going to have 4 plus 12. So fixing my calculation error, this is actually 5 meters per second squared. So if I want to find the tension force, there are two things that I could do now. I could either look at the forces acting on this body, or look at the forces acting on this body. So, sum of the forces equals MA for the 4 kilo mass, or you could write mass 1 here. If you find it useful, you could redraw that with the individual forces. When we're replacing the sum of the forces here, Ft minus M1g is going to equal the mass, that was M1 times the acceleration. So Ft is going to be M1g plus M1a. Okay, I've now gone back and put in the correct acceleration here and fixed up the error I made. It was 6 by 10 to the 1 newtons, not 2. This kind of question I see come up a lot more regularly than the pulleys, I'll be honest. This one comes up frequently because there are so many misconceptions with this. It's part of the reason why I made this as a separate video, because I really wanted to drill in on these two particular examples. If you imagine unfolding this one, it's like we've got a trailer and a car, but the driving force is this force here. That's the force on this mass. So let's call this one mass 1 and this one mass 2. You can imagine if you're going to be putting the shortcut we're about to derive on your note sheet, you need to be really clear about which one is mass 1. Mass 1 is the one on the table or whatever, and mass 2 is the one hanging. So I'm just going to put hanging and table or something like that. You need to be able to derive this yourselves, but I understand that there are circumstances where it would be faster to just use the shortcut on the exam, and I want to empower you with that. So, with this one, I just wanted to point out the normal force and the force due to gravity are both acting on this. They're not helpful to this question. They're just telling us that this force isn't flying up, this mass isn't flying up in this direction or sinking down into the table. So mg and the normal force are not really useful for what we're doing here. What we can see though is there's this tension force that's going to be dragging this 10 kilogram object off the table. And I know it's being dragged off the table because there's no friction being listed here. And to be honest, I very, very rarely, in fact, I don't actually recall a time where I've seen this kind of question with friction. Doesn't mean it couldn't happen, still relevant, but we're going to be exploring it. Everything's frictionless. The pulley, the table, and the mass of the string is 0. So let's look at the forces acting on the 1 kilogram mass. We've got this tension force that's equal in size, but opposite, well, it's actually not opposite direction here. That's a really interesting point. Still equal in size though, because this is the force of the 10 kilogram mass pulling up on the 1 kilo mass. So, with this one here, we've got the tension force, and this has not been drawn to scale because this tension force is going to be smaller than this force, and this force is m2g. So it's like the driving force of this system is the force due to gravity acting on that 1 kilogram mass. And we have the two tensions, Ft, Ft, that are acting on parts of the system. So our sign convention for this one, we're going to make this direction positive. So to the right at the top and downwards afterwards, because we're accelerating in this direction. Accelerating this way, accelerating this way. Again, I haven't actually asked a question here, but I can imagine there's two things that you might be asked. What is the acceleration and what is the tension? And we need the acceleration to be able to calculate the tension here. So let's figure that one out first. So to determine the acceleration, there are two things we could look at. We could look at sum of the forces, three. I've said two when I meant three several times. If we do sum of the forces on this one, the only force acting is the tension, and we don't know that. And remember, we'll be doing sum of the forces equals ma because we're accelerating. Oops, I was erasing. If I look at the forces acting on this one, I've got the tension as an unknown. The tension as an unknown and the acceleration is unknown. So I think it would be much more sensible for us to look at the system because we can ignore those internal forces, the tensions acting on one another. So let's do that. So sum of the forces equals MA for the system. So the only force that is acting that's not an internal force is that M2G. And that's going to equal the mass of the system. Now be very careful. It's a 10 kilogram and a 1 kilogram mass. I'm going to write that as M1 plus M2 and times the acceleration A. Now it's really, really important to note the acceleration of this mass and the acceleration of the system cannot be the acceleration due to gravity. The acceleration does not equal g because we are not in free fall here. Remember, free fall tells us, or free fall means, I should say, that the only force acting is gravity, but the tension force is slowing it down. So a really common misconception is that the acceleration of this object is gravity. It is very much not. In fact, acceleration is going to be less than g. So let's actually calculate it. The acceleration is going to be m2g over m1 plus m2. You might find it useful to draw a diagram like this, very clearly stating that this is mass 1, the one that's on the table, and this is mass 2, the one that is hanging. If you mixed up your masses, you would make an error. So a really handy thing to have as a shortcut on your formula sheet. So let's actually go ahead and calculate what that is here. Oh, a bird just flew into my window. So, mass 2, we said was the 1 kilogram, so 1 times 9.8. I'm sorry for one sig fig again. Mass 1, we said was 1 kilo, plus mass 2 was 10. We're going to keep this whole answer in our calculator, but let's answer this to one sig fig at the moment. 1 times 9.8 on 1 plus 10. So 0.898989. Sorry. 8909090. I'm just going to do 0.890 dot 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 to one sig fig 0.9 meters per second squared. We now need to go ahead and find out the tension. We could either do sum of the forces equals MA here, or we could do sum of the forces equals MA here. Both will give you the same answer because that tension is going to be equal because they're a Newton's third law pair. I am lazy. I'm going to do the 10 kilogram mass because there's only one force acting. So sum of the forces equals MA on the 10 kilogram mass. Only force acting is that Ft, and it's acting in the direction of our acceleration, so it's positive. It's going to equal the mass. The 10 kilogram mass we labelled as mass 1 times A. So Ft is going to be mass 1. Oh, we said it was the 10 kilo here. And the acceleration we previously had, 0.890 dot dot dot. So it's just that value that we had before times 10. So 8.90 dot dot dot. To one sig fig, that is 9 meters per second squared. Oops, no, that was a force, so 9 newtons. Sorry about that. So, things about this question to know. To calculate the acceleration, we ignored those internal forces, which were the tensions. This is a lot like a driving example, where the driving force was the force due to gravity on the second mass. Force due to gravity on the first mass, not relevant to this question here, because it's just counteracted by that normal force. We figured out the acceleration by doing sum of the forces equals MA on the system, and we came up with this nice generalized version here, keeping in mind that mass 1 and mass 2 are as we've labelled them in the diagram. You need diagrams with these questions. This is assuming that we've got no friction and no air resistance. If you did have friction and air resistance, then you could go back and look at the forces acting in a similar fashion to what we've been doing here. I haven't seen many questions that have included it, but it doesn't mean that it's not outside the scope of the course. Then to figure out the tension, we could have done some of the forces on one of the individual masses. Either one, didn't matter. I really encourage you to repeat this question, doing some of the forces equals ma on the 1 kilogram mass to convince yourself of that. You have to get the same answer. Just be careful with rounding. Alrighty, now is an opportunity for you to try this one yourself. Good luck.